Well, we're here now back in section 7.4, but welcome back, everyone. Any questions at all today before we get started? Okay, well, for today's class, we're mostly going to be going through section 7.4. I did make some revisions to the notes on this lecture. There are some problems in there that were monstrously difficult to the point of not being much help on the actual homework questions. So I made a couple changes on there just on the example 3. But aside from that, where we're at so far in the course, after we get through this week, we have another buffer week in the middle here before we get on to our first examination week here. Exams will be held on Monday. And so that means with the way this week is going, I'll be grading around Friday. After grading is done, grades are put in, I start to change gears and I'll be putting in the coverage for the exam 1, the exam 1 review materials and such. So if you're studying early, you'll see these posted probably Friday evening, possibly Saturday if I'm getting a little bit behind on all the grading. Also keep in mind that this is a document of things that will be on the exam. So when you go to write out your page of notes for your exam to support yourself, you could skip those since these would be provided. I should probably close that so not get any weird sound feedback. Aside from that, I think that's the extent of my announcements. We did get the first assignment graded, so grades are now put in. And you can check your grades. They'll update on a weekly basis up here on the Moodle website. But any questions at all, folks, before we jump into the next section? Okay, well, it's another day, another integration technique, but this one is actually pretty special in a certain sense. From section 7.1 to 7.4, those are the major integration techniques that we'll be working on this course. So section 7.5 is where we pump the brakes a little bit, start reviewing some of those techniques before we go on to the last aside topics in chapter 7 on approximate integration and indefinite integrals. So that's where we're at. After chapter 7, we'll be looking much more into applications, things along the lines of center of mass, hydrostatic pressure, that kind of stuff will be what we're looking into majorly. But here's how the note starts. First is really just algebra review topics here. I put down a quick definition of what we even mean by a rational function, since that seems to be what this section is all about. Integrating rational functions. A rational function is, well, when we say rational, we just mean ratio, so you're thinking fractions. It has to be a polynomial in the numerator, polynomial in the denominator, and these are the things we're going to try to integrate. The book is using r of x quite often and q of x quite often. Think of r as the numerator, q as the denominator when that comes up. And yellow is probably not going to work for that. Let's use blue, green. So in the theorem that we'll see below, after example 1, that's what they're referring to with r of x and q of x. I'm not as worried about the degree, except there's one case where the degree is important. If the degree of the numerator is greater or equal to the degree of the denominator, the way we actually start to integrate a rational function like this one is through log division. So we're going to start reviewing log division. Then we'll integrate this function right here. Any questions, comments, or concerns so far before we start on this one? Okay, as it stands, it doesn't look like it's an easy function to integrate at all. In fact, this one would be much, much harder. I'm not too sure what's going on with this one. But here, with the preliminary analysis, what I would say is the degree of the numerator is higher. And so that means we're going to convert into long division. We'll take the x plus 1, divide it into that whole numerator, 3x squared. I like to put a placeholder in my long division, plus a 0x, minus 2. If you're really great at synthetic division, that's awesome, but not all these problems are going to line up well with synthetic division. So I think just ordinary long division is really well suited for this course. If you review this one technique, you're in great shape. Then, if you're like me, it's probably been a while since you've done long division. You might not have done it all summer, so we'll go carefully at first. Here's how I usually think of it. I take the x, divide it into that term right there. So I have 3x squared divided by x. Write the result above. It would just be a 3x altogether. After you get your 3x, think of this as a group where you're going to distribute 3x back inside. So the first step was divide x here. The result was 3x. Take the 3x and come back, distribute it through. X by 3x is 3x squared. X times 3x times 1 is plus 3x. Once we get to this row, we have to do something here. I'm going to recall what it was. Right, so we're changing our signs now. Let me use this as the final sign. We'll subtract here and here. Essentially, I'm distributing a negative sign across to both terms in that group. Take a tally. We'll have a 0 in this location. 0 minus 3x gives us a negative 3x. And carry down the minus 2. Then, if the degree is 1 or higher, we just keep on going. We want the degree of what's here to be the degree of this to exceed whatever is here in order to stop. So rinse and repeat. First, any questions at all, folks, with the first step? Okay, next, we take this x, divide it into this location. We're obtaining a negative 3. Grab your negative 3 and now distribute negative 3 into the group to get negative 3x minus 3. Come back over here and change your signs. Plus and plus now. Take a tally, and we have a positive 1. So that's our remainder, but stating a remainder is not going to help us integrate. What we really want to do is state what is the full result after long division. This entire thing now turns into 3x minus 3 plus the remainder of 1 divided by the quotient x plus 1 again. So this over here is hard to integrate, but because the degree of the numerator was higher, all we really have to do is long division. This is messier for sure, but this is easier to integrate. Any questions, folks, to that stage with just the long division phase? Okay, so back over to the integral. This is going to be, let me maybe scroll down a bit to fit this all in. The integral is now equal to integrate 3x minus 3 plus 1 over x plus 1 dx. Now we've reduced a nasty integral here to essentially a calculus 1 integral in a certain sense. Going left to right, the antiderivative becomes 3 halves x squared minus 3x. And now we need the antiderivative here. Any volunteers for what that one should be? Absolutely, good call. Plus natural log, absolute value, x plus 1. This one's weird by the red dot, but here's a way to think about it with some related examples. This kind of integral can come up quite a lot with what you see here by the red dot. So the first formula you might be thinking of is that 1 over x dx is equal to the natural log, absolute value of x, plus a constant. By the way, I think I forgot my constant. Let's start off on the right track. Don't forget the constant c on that one to finish off the problem. So if it looks like that, you just get this natural logarithm in that way. If you had, say, 1 over x plus 12 dx, let's even put some more in. Let's say maybe you had 5/3 x plus 12 dx in your problem. If that comes up, the antiderivative would be 5/3 natural log, absolute value, x plus 12 plus a constant. And I painted myself in a corner. I'll put the constant down there. So these are kind of nice ones in a certain sense. X to a power 1 in a denominator often implies you're dealing with a natural logarithm, the antiderivative. But it's more this one I would say watch out for. Not so much by the negative, but we're putting in here just for variety. Let's say it's negative 1/2, 5x minus 1 dx. So if I was to do the antiderivative on this one, we could start with, say, negative 1/2, natural log, absolute value, 5x minus 1, plus a constant. But there's something missing right here. Anyone spot what it is? Exactly. If there's a 5 right here, that means when we differentiate this to check it, a chain rule comes up. We'd have to multiply this by 5 in the chain rule. Since it's an antiderivative, we multiply by a fifth to account for it. So most of these are pretty nice, but watch out for a coefficient multiplying x. In that case, we got to negative 1/10. Natural logarithm, absolute value, 5x minus 1, plus a constant. So these things come up quite a lot in this section, and that's just different ways to handle them. Well, any questions, folks, with the main problem? Oh, synthetic division would work on this case, but if we had something like, say, x power 2, you have to modify your synthetic division for every new additional change there. Higher degree means different procedure. So just to be as flexible as possible, I'd say this is a good approach. But if you're fluent in synthetic division, then that would have been faster on this one for that case. Either way would be a good strategy. But if long division is just not something you're a fan of, this would be the method I'd say works for all the problems in this course. Other questions or comments at the moment? I'm pretty rusty at synthetic division. Should we give it a try just for fun? Let's try this out.
Can you explain what synthetic division is? I'm unfamiliar.
Yeah, absolutely. Synthetic division is a way to take that right there and just make it less writing, essentially. So here's how it goes. In synthetic division, if you like this technique, you would take that 1 right there. Let me start all over. The synthetic division technique that I am fluent with requires a coefficient of 1. A degree of 1, so x squared is out, 5x is out. You could factor out the 5 that happens. But if this lines up just right, you take that 1 and change the sign to a negative 1. So that's the first change. Again, this is optional. You don't have to do synthetic division, but this at least answers the question, what the heck is synthetic division? Next, you come over here, you're essentially doing this. But when you really look at that long division, it's not about the x's at all. It's about what happens to the numbers. Let's put in the numbers. They go 3, 0, that's the power 1 term, negative 2. Then you drop a line down, and then a weird little number game begins. The 3 just goes right down. Anyone recall the next step in synthetic division? What happens to the 3 after there? Exactly. Now you multiply this way. 3 times negative 1 would give us a negative 3. We put it right here, negative 3. Now this column is starting to look an awful lot like this column. We have a 0 minus a 3 giving us a negative 3. Tally here, negative 3. That's all synthetic division really is. If you have to divide like this, say, dozens of time in your work, then you start to take out the x's and just focus on the numbers. Next thing, this negative 1 multiplies here. Now it's a positive 3. And this column now looks a lot like this column. The sign flips are already baked in when we do it the synthetic division way. Here we tally this, we get a positive 1. And then once we're done with all of that, again, it's a weird technique, I know. You take these numbers, 3, negative 3, and 1, and notice they go here, 3, negative 3, 1. So again, if you like synthetic division, that's what this is all about. But let's just emphasize purely optional. This is the traditional long division way, which would work for every problem in this course. But other questions, folks, with either the long division, synthetic division, or the main result?
How would you know where to put the x's and like the 1 over x plus 1?
On the synthetic division, you're saying? It would kind of go like this. That's a great question. You look at how you formed these coefficients. It came from here. So this is really the placeholder for x squared, x, and then a constant. So if I'm dividing by x to the power 1, down below would be the coefficients for x, the constant, and remainder. So you just drop a degree, and that's what happened here. X, the constant, and then the remainder divided by x plus 1 again. Weird technique. Again, probably if you're okay with this, stick with it. This is more for people who have done a lot of synthetic division to say it sometimes works pretty fast. Other questions or comments at the moment? Okay, the good news about all these problems is you're probably not going to long divide a lot. I think I have only one problem in the homework where long division is a requirement to get through the problem. And it's always like this. If the degree of the numerator is higher or equal to the degree of the denominator, we must do long division one way or another. But what if it was flipped? What if the denominator had degree 3, say? Long division is not going to help us at all, and we use a different theorem. This is the good old partial fraction decomposition theorem. And let me see if I can fit this in a better way. My results kind of went all over the page here. Let's break that example to the new page and just do a whole new page on this one. So example 2, this is a homework question as well, but I baked the theorem into the example just so that we can work at each of the components as we go. And it's a great theorem. Its whole purpose is to take a function like this, break it apart into components so that you can actually integrate it in a really rapid way. You definitely want to see if a U substitution would work, but it's just out of order on this one. There's no clear way to make U substitution work. So here's what happens in this situation. We have 4 different cases, and in case 1, Q of x, that's referring to the denominator down here, is a product of distinct, meaning everything is different, linear, meaning the degrees are all degree 1 factors. So if that's the case, the split up with partial fraction decomposition looks like this. Now, this could be a potential exam question as well. Watch out for any statement that goes like this. We're just writing down the form of the partial fraction decomposition. We're not going to solve for the coefficients on example 2. We'll do that when we solve these ones, starting on example 3. We'll perform the decomposition and solve for the coefficients as well. So think of example 2 as kind of a warm-up problem. It's also a homework question, and it makes a good exam question only because these are really long problems occasionally. So this is just a way to streamline the exam. So it's really a 67-minute exam. First thing we have to do to this thing is we need to factor it. We need to see if we can get a product of distinct linear factors. So it starts off like this. X plus 5, and I think I didn't really think of the space I needed. Divided by. First thing I'd want to do is just factor out x. So this will be x times 2x squared minus 5x minus 12. Then that denominator factors even further. We have x multiplying 2x, x. I'm going to try this trial and error, so I'll just hope plus and minus works. And with the 12 here, let's see, what could do the job? Sorry, say again? Not quite, because that would multiply to 24. Let's see. We need factors that result in a negative 12. How about 4, 3? Well, what's the check on that? It's been a while since I factored. Let's see. Here to here multiplies, if we're pulling out our answer, to a negative 8x. Here to here multiplies to a positive 3x. The summation is negative 5x. And that's the target we were trying to hit. So that shows we have a good factorization on this one. So that's the first step. We need to factor it down. Now we're ready for, well, let me fix that. Now we're ready for the decomposition. So one thing to keep in mind here is, notice the numerator r of x. It's referring to the x plus 5, but on the right-hand side, it's nowhere in sight. The numerator is not part of what we're about to write out when we're writing out the form of the decomposition. What does matter is that denominator q of x. all the factors are going to get split up in this way. And our author wrote out A1, A2 up to AK because he doesn't know how many letters are going to be used because we don't know the number of terms of the formula. Usually we just use the alphabet A, B, C if we have a lower amount of terms to deal with. So here's how the decomposition goes. We look to the denominator. There's three factors, x, 2x plus 3, x minus 4. All those factors are linear. Their powers are 1, and they're distinct. So we just go a over the first factor plus, didn't need to scroll, plus b over the second factor, 2x plus 3, plus c over the last factor, x minus 4. So that's the form of the decomposition. What we have to also discuss is how do we solve these kinds of things? But we're breaking into this theorem bit by bit. Example 2 is just indicating the form, so we have a good start. In example 3, we'll solve for a, b, and c, and then integrate the total result. So for this initial phase, just writing down the form, any questions at all, folks, on getting to that stage here? Okay, so the partial fraction decomposition theorem is all about this. Finding a way to take something like this and split it apart. That's essentially what we're trying to do. This one had degree 3 in the denominator, degree 1 in the numerator, so log division doesn't help us. But if log division does work, that's the goal. Just split this one fraction into multiple terms, split it apart like that. The decomposition theorem helps us when we can't use long division. So let's go off to case 2 and spot the differences. My part B is a little bit nicer since everything is already factored. But the only thing that's new in case 2 is that some are repeated. If there's a repeat, then instead of the single term, say a over x, they say a1 over ax1 plus bx1, this thing will turn into that. So if it's repeated and it has a power of r right here, then we put in the denominator, first with power 1, then power 2, all the way up to that final power r, whatever it happened to be. Well, that's the format. Let's give it a try in part B. With part B, again, this one's nice. It's already factored. It's all about the denominator for the moment. But notice the first factor, x minus 5, just gives us a over x minus 5 to start. But it's this right here, which put us into case 2. The second factor has a multiple of 3, so we've lost distinct linear factors. It's being repeated. So if the multiplicity is 3, then we go like this. Start off with power 1. Now we start bumping the powers. We'll go x plus 7 to power 2. And we know when to stop when we reach that power. Power 3 is our stopping point on this one. So it'll be plus d over x plus 7 cubed. So that's the form of that decomposition there. Any questions, folks, with getting to that one? Okay, does it make sense to folks so far? Awesome. So carrying on, or sorry, go ahead. Oh, what was your question about this part? How did it go in here?
So 7 to the power of 2. And how did you get to the other part?
Well, this power right here is 3 rather than 2.
Oh.
The zoom might have been weird on that. Yeah, let me try and get a better zoom going. Yeah, this one was to power 3. Sorry about that. Was that what your question was about, really, on that one?
Yeah.
Gotcha. So whatever this power happened to be, you start at power 1 and end on that particular power. Any other questions at the moment?
So
Okay.
is a good rule of thumb on these, like if your numerator is bigger than the denominator, it's just you divide and then it's partial fraction if your denominator is bigger?
Absolutely. Yeah, that's the best rule of
Okay.
thumb. So only use partial fraction if essentially the denominator wins. How did they say it? Assume we have a rational function, r of x over q of x, where the degree of the numerator is less than the degree of the denominator. Essentially what you said, but that's a lot of words to say that. Better way to think of it is if the degree is higher, down below, use partial fractions. Otherwise, long divide, just as you said. So this one had degree 3 up top. Denominator on this one would have been degree 4. So we're on the right track for this problem. However, if that was a power 2, none of that's correct. Long division is the first step. Any other questions or comments so far? Okay, so that's 2 cases so far. Next, the new thing in case 3 is this word, irreducible quadratic. What's an irreducible quadratic? It's something you cannot factor unless you're using complex numbers, is one way to say it. But in this calculus course, we're focusing on real numbers. So another way to say it is your quadratic is irreducible whenever the discriminant is negative. So you could use that as an overall test there for irreducibility, but a lot of times these are pretty clear they should be irreducible. Take this one, for example, x squared plus x plus 7. If you were to factor that, well, there could be a way using square roots, but it doesn't look like there's much you could attach to. So you could track out the discriminant. The coefficients go 1, 1, 7. So here, b squared minus 4ac becomes 1 squared minus 4 times 1 times 7. Yeah, that's 1 minus 28, so it's negative. And that tells us this is irreducible. So irreducible quadratics are a pretty interesting thing to come up. Whenever that happens, you take this portion here, and that's going to be the term that you attach to the decomposition. The numerator will have a degree 1, so we use 2 coefficients to fill out that numerator. So writing this one out, there is 2 denominators on this one, so we begin by just saying a over x minus 5. But then when we go to the irreducible, we need 2 more coefficients, so it should be a bx plus c over here. Divide by x squared plus x plus 7. So this is the part that's new in case 3, irreducible quadratics. Any questions, folks, with that case at the moment? So definitely riveting stuff. It's not clear how this helps us to integrate until we can actually solve those coefficients. So that's always the main test with the decomposition. So once again, think of what we're doing right here as really just a warm-up. We're first thoughts looking at this theorem. Finally, here's case 4. There's one difference from this case and case 3. And let's see here. There we go. Notice in case 3, they said you have an irreducible, but no repeats. Now in case 4, it says there is a repeated irreducible quadratic factor. If the repeated irreducible quadratic factor has power r, then you start out at power 1, bump it to power 2, and so on, until you get to the rth power. So we handle case 4 just like you handle case 2. Only difference is you're throwing in 2 terms in the numerator with a degree 1. So that's what's going on with this one. X squared plus 5 is absolutely irreducible. Here's another way to test it if you're not a big fan of the discriminant. X squared plus 5 equals 0. If you can solve this and get a real number, it's not irreducible. If its only solutions are complex numbers, it is irreducible. So imagine solving that equation. We'd have to subtract 5. You would take the square root, and then x would be positive or negative root negative 5, which would be positive or negative I root 5. Now we're in the land of complex numbers, and this tells us x squared plus 5 is irreducible. which is almost not fair because if you're thinking of x squared minus 5, that one is reducible. You just go x plus 5, x minus 5. So x squared minus 5 is reducible. So, or factorable is a fine word to use here. Irreducible is just a word that comes up in other algebra contexts. So here, we have an irreducible to power 2. Yeah, go ahead. Oh, sorry, you're absolutely right. I should have went the root on that one, root on that one. Thanks for spotting that. Not sure why I was thinking 5 would have worked. Yeah, with the root, that one will work out. I should have taken the square root of that value. Other questions at the moment? Okay, so part of the work of deciding if you're in case 1 through 4 is knowing if you even have it irreducible. Quadratic works just fine if you like to use it. Also, this is a good thought as well. If you can factor it with real numbers, then you're dealing with something that's reducible. If you cannot factor, or if you cannot solve it set equal to 0, it's irreducible. So that's this piece right here. Here's how we'll handle it. It's degree 2, so we need 2 terms that go like this, starting off with the ax plus b. Down here, we begin with power 1, so it's just going to be an x squared plus 5. Then we keep on writing down these terms until we get up to a power of 2. So the next one is going to be cx plus d divided by x squared plus 5 to the power of 2. So now we have that nailed down. Last thing we have to do now is grab that denominator. That's degree 1, so not irreducible. We just say, sorry, say again? Yeah, just an e on this one over the 3x minus 8. Good call. So that's how this one would decompose. Again, the hardest thing about all of this is solving those coefficients. Sometimes you have to actually use matrix algebra to make this happen. Other times, it's not as bad. The ones that we're going to focus on is really just the cases where we don't have to use linear algebra to solve a system of equations. We can get the solution more readily. Well, that's our detour of discussing the, what was this theorem called? The partial fraction decomposition theorem. Any questions at all, folks, with either of those cases? Okay, and just a reminder, just to make the homework bearable, I assigned a problem just like this one. So watch out for those instructions. If they tell you not to determine the numerical value of the coefficients, they're meaning your answer ends there. We're just looking at the format. So what we're going to do next is go beyond, and example 3, we need to do the decomposition and integrate all at once. Well, any questions whatsoever, folks, before we start with the main questions here? Awesome, let's give it a try. Well, first question we have to ask ourselves, do we need long division on this one? Absolutely not, you're right. The denominator is of higher degree, degree 3. If there was a tie, we would have. Actually, I only have one long division problem in the notes. It was the first one. I think there's only one in the homework set as well. So first thing I'm going to do is start off by writing 2x plus 5 over, oh dear, that. Let's begin by factoring. We can factor out a 2x this time, so it's going to be 2x, leaving behind x squared minus 5x minus 14. We have to factor even further, so now it's a 2x plus 5. The trouble with that one is it is reducible, so let's see. It should go as x, I'll go plus, x with a minus. Anyone see the coefficients for the factorization here?
2 and 7.
Yeah, that would do the job. I like these ones. They're a little bit faster to factor. The first factoring problem we did was a little bit more gnarly with trial and error. But on exam questions, I like to streamline it. So factoring shouldn't be something stopping you. We want to focus more on the calculus on an exam setting. This is more in typical what a homework problem might look like. Once we get to this form, we start writing down the decomposition. There's three linear factors. They're all different. So it just goes a over the first factor, b over the second factor, x plus 2, and then c over the last factor, x minus 7. So now that we have this equation, the decomposition is ready to start. And I usually don't always write down this step, but it's important to see it at least once. So I'm going to put it in the notes just so we can visualize it. We need to clear out this denominator to get started. So this whole denominator is going to be multiplied here. 2x, x plus 2, x minus 7, here, and here. Which means it's also multiplied on the left-hand side, but that's going to cause a full cancellation of the left-hand side, just leaving 2x plus 5. Now on the right, we cancel and just write down what's left behind. Here 2x is canceled, and we just have a times x plus 2 times x minus 7. On this one, x plus 2 cancels, so this is plus b multiplied by 2x times x minus 7. Finally, on this one, x minus 7 cancels, so it's plus c times 2x times x plus 2. Good to double check these. And if you don't like writing out this stuff in orange, then another way to think about it is, if you see a 2x here, that's canceled, and you just bring in those two, x plus 2, x plus 7, multiplying a. Likewise, x plus 2 here means you have the full denominator except the x plus 2, and so on down the line. X minus 7 is missing here. So once the denominators are cleared, we're about ready to solve for coefficients. Any questions, folks, to that stage? Okay, the problems I assigned in the homework essentially all go this way. I didn't go for problems where we had to use the method of equating coefficients, only because the algebra gets so out of whack for those kinds of problems, it becomes less of a real question you would actually do. For problems like these, in other words, how would people solve A, B, C, and D? This one's really hard. They would probably just use a computer algebra system in practice to solve for those coefficients. So we're going for the ones that are reasonable to solve by hand. Everything that goes kind of beyond this is more suitable to software, or you can write down a system of equations if you've done linear algebra to make it work out. So here's how we'd start off this one. This is a polynomial, and as soon as you choose a value for x, you have a brand new equation. A nice choice for x could be, how about, well, you have a lot of good options. How about 0? If you plug 0 here, you've wiped out b coefficient and the c coefficient. So let's write that in. X equals 0 implies, this arrow is just a quick way to say implies, or this statement implies the next equation. Left-hand side is now 5 equals, here it's going to be a times 2 times negative 7, and everything else is dead in the water, thanks to x appearing as a factor. So now we have an equation for which we can solve a on. This implies 5 equals negative 14a. So finally, this means a equals negative 5/14. So 1 down, 2 more to go. Does that make sense to folks on the strategy for this one? Okay, notice also what's weird about this. We haven't even touched the integral. All of this is pure algebra, but once we get through it, we can finally return to the calculus. So we need a good next value for x. Good choice. I mean, anyone could pick 5, and you can make that work, but you're working a lot harder. You might have to solve a system of equations. But I like your choice of 7, because it wipes out the a coefficient, the b coefficient. You're solving for the c coefficient with that choice. So let's say x is 7. I'm starting to realize I need a calculator for this. Okay, so here's our support in case we need it. So if x is 7, we're going to have 14 plus 5 on the left. That's not so bad. 19 equals. This term is gone. This term is gone. And here we're going to have c times 14 times 9, and let's treat ourselves to a quick computation. So we have 126 times c right here at that stage. Nasty numbers on this one. So this implies 19 equals 126 times c. So that then implies c equals 19 126ths. Let me highlight these so we don't lose track of them. But that's 2 down, 1 last to go. Any volunteers for the last best choice for x? Absolutely. Let's take x is -2. That would give us a -4 plus 5, so a +1 is now equal to a coefficient's wiped out. The b coefficient's alive, so this will be b times -4 times -9. Let me know if my numbers go sideways. C coefficient's wiped out. So now we have an equation that reads 1 equals 36b, which then implies b is 1/36. So there's all the coefficients. What made this one kind of nice is the decomposition is case 1. Case 1 can always be solved very directly in this kind of way. Plug in the right values, get an exact answer for every choice you make. Sometimes it gets a little bit more dicey, so we have different cases we're going to take a look at. But another reminder is this is the start of the problem. We take all that information and say that the integral, let me call this I just to connect the, well, maybe I is not a good choice. I already have an I here. I'll just write it out this way. 2x plus 5 over 2x cubed minus 10x squared minus 28x dx becomes, scroll a little bit to reveal the next step. We're going to write this in, but in place of a, b, and c, we just throw in the coefficients we have just found. So the original integral, copied here just so we know what we're working with, becomes, first as a, that's going to be -5/14 divided by 2x. Now next for b, we have plus 1/36 divided by x plus 2. Then finally for c, 19/26 or 126, really wonky numbers on this one, divided by x minus 7 dx. So those are the numbers all plugged in. All we have left to do is just integrate those 3 different terms. So that's the partial fraction decomposition working for us. The original integral is not easy to do directly without this preliminary step. Any questions at all, folks, so far?
Question, so consider if we plot at different numbers instead of x equals to 0, 7, and -2, you still get the same numbers?
You would get the same numbers, but you would have 3 different equations, potentially all involving a, b, and c. But that means you're just dealing with a system of linear equations. Directly solve that, row reduction, you get the same results. But for these, this is just definitely the faster way to go. Either way would work. Yep. Other questions at the moment? Okay, well, let's start by integrating all of this. I think the first term is the toughest one, actually. If you were to integrate this term, think of this as a -5/28 when you're involving that denominator. Multiply by the natural log of the absolute value of x. Let's pause right there. Does that make sense to folks on how this came into be? Okay, and just in case it looks a little bit weird, here's another way to think of it. You could rewrite this as integrating -5/28 times 1 over x dx. That's how I would think about that problem there. The coefficients kind of get all messed up around, but in this terms, the antiderivative is quick and immediate. I think that's the trickiest one, but going off, these ones are not too bad. This is 1/36, natural log, absolute value of x plus 2. Then move off to the next, plus 19/26, no, 19/126. natural log, absolute value of x minus 7. Add a constant, and then that's the full story on that one. It's a bit of a mess for sure. And one thing that's also kind of dicey about this is sometimes the back of the book likes to use properties of logarithms to start simplifying, compactifying this kind of stuff. In this course, you don't have to ever do that. So when you look at the solutions to section 7.4 to the odd problems, I often let the problems like this just to indicate this is an okay stopping point in our course. You don't have to go wild on properties of logarithms to simplify it. Unless you find it fun, then I'd say go for it. See if we can zoom out for the whole problem. It's pretty much here. There's the integral. So what we're going to do is just practice a few more of these style questions. So here's our next one. This one's a definite integral. And what case would you say we're in this one? Is this case 2 or 3? Absolutely. What makes it case 2 is that polynomial in the inside of that group is linear, degree 1. So we have these two distinct, but this one's repeated. So case 2, as you said. So let's say here, because of that part, we're looking at a case 2 type problem. Starts off as before. I'm going to ignore the integral and just focus on the decomposition first. X squared plus 1 divided by. This problem is nicer because the denominator is already factored. So let's just write in x minus 3, x minus 2 to the power of 2. That right there, again, is what makes it case 2. So we go a over x minus 3. And any volunteers for what the last two terms should look like?
B over x minus 2, then c over x minus 2 squared.
Yep, absolutely. Thanks for those. Essentially, we just take the other distinct factor, if its power is 2, rewrite it twice, increasing the power all along. So we've got it, folks. That's the form of the decomposition. Now we clear the denominator. Just for visualization's sake, and also to show what's happening in the notes, I'll continue to write this step. We're multiplying by x minus 3, x minus 2 squared here, here, and here. We're also multiplying it on the left-hand side. That leaves behind x squared plus 1. Now on the right, we'll have 8 times x minus 2 to the power of 2. B, well, here we cancel off 1 power of x minus 2. So it's x minus 3 minus 2. Sorry, question first, Cash? Well, then for the last one, x minus 2 will cancel that one entirely. Just leave a c times x minus 3. This time, the strategy that we used doesn't go exactly as smoothly as it did on part A with case 1. It's because of the repeat right here. But it's still not too bad to get it in. Here's what I would still do. Just pick the best number you can think of. X equals 2 is great because it kills that term. So let's go for x equals 2. I don't want an equal sign, that gets confusing. Let's use that symbol to convey next step would be 5 on the left equals a cancellation, another cancellation, and we just get a negative c. That's kind of nice. It means this one's basically solved. C equals negative 5. So that's 1 down. Now, the next best choice, and we're running out of best choices, is positive 3. So if we pick x as positive 3, we'll have on the left 3 squared plus 1, so a 10. Here we're plugging in a 3, so that's 3 minus 2, giving us a 1 squared, still a 1. So this is just 8 times 1. And for the rest of the terms, these are cancellations. So now we can just say, the solutions are kind of there, but I'll just write it again. A equals 10 looks a little bit prettier. And now A is determined. But here is, again, where case 2 gets a little dicey. There's no nice, clean choice for the next number. So we're looking for just the next easiest number to use. what would you say the easiest number is to plug in that equation? What would cancel the most stuff? Is another great question you might have.
0.
Zero is a good choice. If you plug 0 in, just about everything really comes down to not too much left. So let's put in x equals 0. It's going everywhere x appears on this, so we'll have a 1 on the left-hand side equals. Here, we'll also notice you have the value for a. I'll plug it in on the next step and call this a times -2 squared, so 4. But we have that value. That's just a 40 now. Then we're plugging 0 in here. B is the one that's undetermined so far. We'll have a -3 times a -2 when x is 0. Then it'll be c times -3 when we plug a 0 in that location. So this case 2 wasn't so bad, but you can imagine if that power was like a power 3 or a 5, you would have to use system of equations to solve this one, because you start to lose enough equations where you can substitute in the prior information. So this one is just nice to run through. We have 1 equals a times 4, but a is 10, so that's a 40 in this location. This is going to be plus 6b. Let's see. C is a -5, so this is just a positive 15. And that equation definitely looks not so bad to solve. We can run it through. We have 45, so 1 minus 45 will give us -44 is 6b. Divide by 6, that's kind of awkward. We'll get b equals -44/6. Let me double check my numbers. They suddenly feel kind of weird on this one. 54. Yeah, I had 55 minus, that was a 54. Thank you for spotting that one. I think it's just too late at night for me to do any arithmetic. I should have pulled the calculator up on that one. So 54, 54. Now that one suddenly feels right. That's now a -9. But also keep in mind, sometimes the numbers are just messed up, and that's how they go. That's why I put this problem here as well on the notes. A lot of the problems that I like to write on a real honest exam go a little bit more like this. Again, the exams need to be streamlined since they're timed. And so you should expect clean numbers like this on a real timed exam. So we've got it, folks. That's the decomposition. Yeah, go ahead. Oh, let me double check. So I had a -5 here. I was plugging 2 into this location and this location. So I should have got a 2 minus 3, so a -1 right here. And a 2 here would have given me the 5 that came down there. So I just divided by -1 to get that value. Other questions at the moment? Okay, it's not going to work out this way on the notes, but sometimes it's kind of fun to visualize it this way. I'm going to delete this in just a moment, but this is what we've done. You can now integrate this, which means you're just integrating this and plugging in the numbers you just found. So it's kind of neat to see how it all comes together. Just a little bit messy on the paper to do it that way. So I'll take another step and carry it down. So here's where we reconvene. We're integrating x squared plus 1, x minus 3 times x minus 2 squared dx. And coming up here, we're just filling in the information. We'll start with a came out as a 10. So 10 divided by x minus 3 plus b. B is a -9, so I'll go minus 9 divided by x minus 2. Lastly, the c up here, I'll throw in the -5, so we'll go minus 5 divided by x minus 2 squared. You know, if we're dividing by x minus 2 squared and we're looking for an antiderivative, I propose this is probably the best way to write it. X minus 2 to the power of -2 just makes finding the antiderivative a little bit nicer. Still the same function, But here it reveals what the trick is in getting the antiderivative a little bit better. So that's finally our big step. And look, this was a timed exam. You just ran out of time here. This was a 6-point question. To me, that's 4 out of the 6 points. This is the major thrust with this section, knowing how to navigate through the decomposition, knowing its correct form. So the majority of the partial credit is really all of that. Still, we have to finalize it, so we'll run through the integral down below. So going left to right, really it's just more of those logarithms like we saw before. Let me first move this down a bit. On the first one right here, we'll get 10 natural log absolute value of an x minus 3. Then just rinse and repeat on this one, minus 9, natural logarithm absolute value of x minus 2. Here's where it gets interesting. This is to a power of negative 2. So the power increases to a negative 1. Divide this by negative 1. That's a positive 5. X minus 2, power negative 1. Good one to double check. If you differentiate this, power comes down. It's a negative 5. Power drops down by 1, making it a negative 2. Last thing to remember is the constant. And we did it, folks. That's the decomposition of that integral up here. It's hard to show the whole thing. Oh no, you're right. I forgot all the way up here. We're going from 0 to 1. Let's fix that. Let's see, what's a good color for this? Let's just use yellow. Integrate from 0 to 1, which means I should have remembered 0 to 1 on this one. Just sort of stuff it in there. 0 to 1 fits a little bit better on this one. If it's a definite integral from 0 to 1, you don't need the constant integration. You're taking this whole thing and evaluating it from 0 to 1. So that's our very next step. This is just a lot of writing. So first you're plugging in 1 inside here. You'll get 10 natural logarithm absolute value of a negative 2. If you wrote this as natural log 2, then you're saving a step on that. But I'll write it this way first to start. Plug a 1 here. Negative 9 natural log absolute value of negative 1. This one would go to a 0, but this is what it would look like in the first step. And for this one, this would be plus 5. I'm going to bring this base down, so it's going to be x minus 2 in the denominator. The x is a 1, so 1 minus 2 down below. So that takes care of the upper limit of integration. Rinse and repeat for lower limit. That look right to folks so far? Okay, now 0 is plugging into all this stuff. We'll get 10 natural log absolute value negative 3 minus 9 natural log absolute value negative 2. Here, again, I'm going to take this x minus 2, put it in the denominator, plug in 0 for x to get plus 5. 0 minus 2. So now it's a whole bunch of mess of logarithms. Let's see if we can simplify it just a touch. 10 natural log of just 2 after computing the absolute value. That's a cancellation because it's natural log 1, which is 0. This is minus 5. Here, I'll distribute the sign and write down the logarithms. This will be minus 10. Natural logarithm of positive 3 after the absolute value. This will become plus 9. Natural logarithm of a positive 2. This is a minus 5 halves, so distribute and we get plus 5 halves. That means I have like terms. I'll take one more step. So the answer I would probably end on in this course is 10 natural log 2. I have negative 10 halves plus 5 halves, so that's a minus 5 halves.
We add up the 10 natural log 2 and 9 natural log 2.
Oh, geez, absolutely. I have 9 log 2, 10 log 2. And let me double check that. That should have been a 9 log 2. My numbers feel weird all of a sudden. Let me take another look at this. I plugged in a 1 here and I got to negative 2, negative 1, 0 here gave me negative 3, negative 2. Yeah, I think my numbers are right here, but that's definitely a mistake of those like terms. Let me fix that there. So it's 10 log 2 combined with the 9 log 2 for 19 log 2. then minus the halves, minus 5 halves rather, minus 10 natural log 3. And then I'd say this is a good stopping point for this question here. Thanks for spotting the like terms on that one. But other questions at the moment?
I had a quick question on natural logs.
Yeah,
So when you're integrating like I guess it's like 1 over like x, that will become there's sorry, I guess I'm asking a question on the coefficients. So
oh, gotcha.
when you integrate, does the coefficient of x disappear from the ln? And it just becomes 1 over the coefficient ln of x?
Uh, depends on how you mean. Let me double check. Are you meaning, say, a problem that goes, say, like this one here? Integrate, maybe
Yeah,
it's like a 1/5x minus 1.
yeah. And so like if that 5x, when you integrate that, that just becomes 1/5 ln of x minus 1.
Yeah, absolutely. It would still be the 5x minus 1 like that.
Oh, gotcha. So the coefficient still stays. It just becomes 1/5.
Exactly, yeah.
Okay.
That way, when we differentiate this, 5x minus 1 still goes in the denominator, but then you multiply it by the derivative of this, which is a 5, and that's why we needed that 1/5, like you said.
Gotcha. Okay, that makes sense. Thank you.
Yep, absolutely. Other questions at the moment? Okay, so this is partial fractions in a nutshell. On a real exam question, these are tough to actually ask because as you can see, this is a lot of algebra where if you make a mistake, maybe on the decomposition, maybe on the factoring stage, it's like a hard wall where you can't really go too much further. So I might ask one of these on a real exam, but you should also expect this is the more likely exam question. And on the homework, that's when we're going beyond and completing everything, pushing through, solving the coefficients, and doing the integration as well. But again, these are some really long problems. And most of the time when people are doing this kind of work, they use a computer software to actually solve for these coefficients, unless it's a nice situation where things are aligned just so. Otherwise, the algebra really gets out of hand on these kinds of problems. That's why I have a revision on this one. I had this one to power 2. It looked like a fun problem until I started to solve it this morning when I was practicing. That part in red to power 2 means it's now a system of equations. You really need linear algebra to solve the coefficients on this thing. I didn't assign anything like that on the homework, so we'll make this one our last question when we come back on Thursday, just taking another look at the decomposition. Then we'll move over to the next section 7.5, which is a review section essentially. Well, I think this will be a good stopping point for us, folks. I think this question takes like 15 minutes or so. But any questions or comments then on what we've done so far? Okay, well, have a great night, folks. I'll see you all on Thursday's class. You betcha. Any questions?
I don't really remember much. I don't remember too much from derivatives. The TikTok one a while ago.
I feel you. Yeah, I understand.
Why doesn't x minus 2 to like why doesn't that equal some sort of natural law?
That's a good question. So the issue with that one is that 1/x minus, or that x minus 2 integral. Let's put it over here and just leave it on the notes. That's a really good question. You have something that looks a lot like this, essentially, versus something that could look like this one, 1/x minus 2 dx. So this is the one we're dealing with in our problem. But if you're dealing with this integral right here, what you really want to do is say that this is the integral x power negative 2 dx. When you integrate that one, power here goes up. So you add 1 to negative 2. It's x power negative 1 now. So you divide by negative 1. add the constant, and then reconvene. This is altogether -1 over x plus a constant. But the real answer to your question is, if you took that and differentiated it, what would you get? Well, that one is kind of a nasty derivative. You'd probably think of it in terms of -1, or excuse me, negative x power -2 plus a constant. Then the derivative of this one would involve, or hang on, that was -1. Sorry, it's turning into a long explanation. There we go. So back on track, I've got a -1 here. Differentiate that, and the power rule says the negative multiplies here, so it's positive. The power goes down by 1, so now it's -2, which is 1 over x squared. And that gives us right back to our integrand right here. So there's only one function you can differentiate up to a difference of a constant that gets you back to that one. And the wild thing is, if it's a 1 over x, this one is always the natural logarithm of absolute value of x plus a constant. Essentially, there's nothing we can come up right here that looks like that, a power of x, that results in the 1 over x after we differentiate. So that's the trouble with this one. And if it's x minus 2 to power 2, really it's the same kind of idea. We're going to land to a problem that looks like that, except it would be 1 over x minus 2 to the power 2, or hang on, x minus 2 like that. Should look about like these right here. The extra negative sign plus a constant. So anything that looks like this always goes to that stage in the answer. But if it's just x to the power 1, these are the only ones that give you the natural log x. Unless it's something like this, where maybe it's like x over maybe x squared plus 1 dx. This one is actually a logarithm as well, but you have to show that by u substitution. This turns into the natural log, absolute value of x squared plus 1 plus a constant. So if there's extra variables here, it can go back to the natural logarithm. But if your numerator is just a coefficient of 1, and the power is not a 1, these are the ones that do not turn into a natural log. It's got to look just like this, a power of 1.
Yeah,
Well, does that make sense for the overview of those?
kind of. It's just because after if you would antiderive it, the power would go to 0. And
Yeah, that power rule here just breaks
Yeah.
down entirely, which is kind of mysterious about all this. So the natural log is either in this case with power 1, or in this case where there's extra variables, allowing a u substitution to give you a natural log in the answer.
there we go. Yeah, that makes a little more sense.
Awesome.
I also emailed you a couple hours ago, just for one of the questions on some point 2, I think. So I just emailed you for if this answer
Yeah.
was equal to equal to
Secants on that one.
yeah.
Looks like I used a secant on my substitution for 29. Did you use a tangent on yours?
Yeah, I did. So,
Yeah, you'd get a totally different looking answer. But if you navigate all your steps correctly, your answer is just as equivalent.
yeah, to me, my math looked right.
Yeah, let me double check for you. So if you have tangent, you get secant squared. It's going to leave secant power 4. Tangent cubed becomes u cubed. So secant power 4 means you're going to get tangent squared plus 1. So that's going to be, yeah, that'll be 1, 2 tangent squared, tangent 4. So 1, 2u squared, u power 4. So that's u7, 5 cubed, 8, 6, 4, back to tangent. Yeah, I think you're on the right track with that one. That one looks
Yeah.
great.
Okay,
That's kind
I
of
was-
annoying. There's two approaches. Your answers look totally different, but they're the same
Yeah.
function.
I knew that it could make different stuff, but because my math was right, I would just wanted to email you to see if it was
Cool.
also right.
Yeah, you're on the right track with that one.
Where did I move my pencil?
Uh-oh, I've got one here, but,
No, I said in my pocket.
gotcha.
Yeah, I didn't know that. Alright, I'll send it this time.
Sounds great. Thank you.